Hi, welcome back. We're in Lecture 16, Segment 2, on analysis of variance. The topic in this segment is post hoc tests. As I showed you in the first segment, we can get an F ratio which tells us if there's a significant effect somewhere across our groups, but it doesn't tell us which pairwise comparisons are significant. That's what post hoc tests will do for us. So post hoc tests such as Tukey's procedure allow for multiple comparisons, but they don't inflate the probability of a type 1 error. So they're constructed to protect against that inflation of type 1 error by adjusting the p-values. As a result, there are lots of different procedures. So Tukey is named after John Tukey, a statistician who actually worked here at Princeton. And there are a slew of procedures that all vary slightly in how they do this adjustment. So I'm just going to mention a couple of them and show you that they vary from what's called liberal to conservative. So liberal would be just not doing any adjustment whatsoever, and conservative would be sort of the most heavy, stringent adjustment you could come up with. And I'll show you a range. So as I said, there's many procedures available. If you want to Google an R, there are lots of different functions. If you've looked at other software packages like SPSS or SAS, ones that are sort of menu driven, you can click on post hoc tests and then you have sort of 20 buttons available for you to click. You just pick one. I'll talk about a few and how they differ and why. Again, the most liberal would be to do no adjustment, which is sort of inappropriate. To the most conservative is Bonferroni's procedure, which is a relatively well-known procedure. If not often used, it's maybe not as often used as Tukey's because it's so conservative. Now, just to remind you about NHST and the problems inherent in NHST, remember that I set up this matrix where there's one of four possible outcomes will always happen when you engage in NHST. And think of the rows in this illustration as sort of alternate universes. So you either live in a world where the null is true, or you live in a world where the null is false. Let's for a moment assume that the null is true, that you have no effect going on whatsoever, which might be the case for working memory training, right? So let's assume there's just no effect at all. We can estimate the probability of type 1 errors, right? We set that by setting alpha. So we set it to say 0.05. And that's convention because we can all sort of live with about 5% error rate. What that means is if I have this family of T distributions or family of F distributions, if there's really nothing going on, if there's no effect, but say I just do the experiment over and over and over again 100 times, then 5 times out of 100, I'm going to get a fluky outcome, one that's way out in the periphery, and I'm going to claim that there's a significant effect, and that's a false alarm, right? Even if the null is true. So that can happen anytime we engage in NHST. So now think about these situations where we're doing multiple pairwise comparisons in our post hoc test procedure. We're inflating the probability of those type 1 errors happening. So we have to build in an adjustment. And that's what these procedures do. So let's look again at this working memory training example. Here is the output I showed you in the last segment. And at the bottom is Tukey's procedure. The logic behind Tukey's procedure is he assumed that what most researchers are going to want to do is engage in all possible pairwise comparisons. So he just corrects for that many comparisons. You could do more than that, right? You could combine groups and compare them to another group, but he stops at just all pairwise comparisons and corrects for that many. And here you see the p-values. Again, I'm going to compare that 17 days versus 12 days p-value to the results from the independent t-test where there's no adjustment. And now let's compare that to the Bonferroni procedure. So we'll do this in lab. There's a function in R called p-adjust, and this is a way to adjust your p-values where you can put in a p-value. So this p-value that I entered into the p-adjust function came from the independent t-test because that was the uncorrected. The method I put in was Bonferroni. Again, you can look this up in R. There's lots of methods, but I put in Bonferroni. And there were 6 possible pairwise comparisons in this example. So that's another argument that the p-adjust function takes, and it returns the adjusted p-value, 0.04. So now let's just compare those procedures. So the independent t-test, there's no correction, so that's most liberal, gave me a p-value of 0.0067. So even if I wanted to be really conservative and put my alpha level down at 0.01, this would still be significant because it's less than that. Then you see a big jump, relatively speaking. I know these are small values, but if you're worried about getting under p of 0.05, then you're starting to get a little worried here, right? So the Tukey procedure gives you a value about 0.03. Bonferroni, you're up at 0.04. So in all cases, it's still a significant, statistically significant difference, but you see that the p-values change as a function of the procedure that I ran in R. Again, the independent t-test, most liberal and actually inappropriate in this example. Bonferroni is going to be the most conservative. Tukey is probably a nice happy medium and pretty popular, pretty common. So to wrap up this segment, we have post hoc tests are necessary after you do a one-way ANOVA if you have a significant effect, right? If you don't have a significant F ratio, then you're not going to engage in this procedure because no pairwise comparisons will be significant. And the way they work is they adjust for that inflation and probability of type 1 error.